my favorite topic, primal heuristics. I've worked on this a lot, some would say excessively, over the past 20 years. And yeah, I coined this talk where MIP solvers roll dice. You might see why in a bit. Interesting. That's my presenter view here. Such a nice introduction, and then nothing. Give it one more try. That looks more like I want to have it. Okay, so heuristics. Let's first look into the general idea and talk about what information general heuristics for general mixed integer programs use. We will not talk at all about problem-specific heuristics here. You've probably seen a lot of this in your, or some of these at least, in your OR classes. If not, don't worry, doesn't really matter. But we are talking about general heuristic ideas for general mixed integer problems. And then we will look into three main different categories of heuristics and talk about my favorite measure of how to evaluate primal heuristics. Okay, back to our MIP solver flowchart. You see, I put in heuristics twice here for the main points where they are applied. Knowing how solvers look internally, this would be the much more correct pictures here. You can apply heuristics before presolving, after presolving, after the AP, but before your cut loop, during your cut loop, after. Note when backtracking, in the background as an own parallel task of its own, running completely independently of the branch and bound search. There's so many possibilities. A lot of this, if not all, is done in solvers. And heuristics may trigger other heuristics. So there should be like some three-dimensional zoom in effect, whatever. Okay, but what are primal heuristics? So primal heuristics are incomplete methods, unlike cutting plane method or the branch and bound, which is a complete exact method of solving a problem. They are incomplete. That often find good solutions, not always. At times, they might not even find anything within a reasonable time without any warranties. So neither of whether it finds anything or they do not provide any bounds, any dual bounds to the problem, just good primal solutions, hopefully. Okay, my last chemo, we talked about complete exact algorithms. I mean, those are all that we need. Why do we want to work with such unreliable methods if we know how to solve the problem exactly? There's a couple of good reasons to do so. They often can prove the feasibility of the model very quickly. That's very useful for you as a modeler. You might notice during your career that more often than not, the first model that you write for something is wrong. You forgot some constraints, you did whatever kind of mistake you can do. So if a solver immediately provides you with a feasible solution and not takes hours and days to solve the problem, you can quickly check it and see whether it looks like what you would imagine a solution to look like. So that's good. In practice, nearly optimal solutions that are within 1–2% of optimality are sufficient most of the times. So if for nothing else, then because often there's imprecision in your data. I mean, let's think about the optimization of a traffic network. Do you really know how many passengers go from one place to another at one particular day? Obviously not. So you're working with estimates and approximations anyway. And then the nicest argument for us here in this class is the algorithmic argument that feasible solutions guide the remaining search process in different ways, starting with the bounding step of your branch and bound algorithm. If you can already apply bounding before starting the, if you already have a bound to use before starting the tree search, how cool is that? That can and will be useful. Okay, primal heuristics might be a good idea after all. What kind of information can they use in a general MIP? There's a couple of different things, not that super many actually. And I would dare to say that the majority of heuristic algorithms use some combination of these, plus the ones on the next slide. So the current LP optimum certainly is a good starting point for whatever kind of search procedure you would want to do. The current incumbent, so knowing, the current incumbent, knowing one good solution to the problem might very well help in constructing other good solutions or even better solutions. Other feasible solutions that you found earlier during the search process still might be useful to derive some information from the LP optimum at the root node as opposed to the local LP optimum. And then finally, there's like one or two procedures, couple of procedures, maybe more than two, that use the analytic center. I won't go into the detail. Think of it as something like the center of mass, the center of gravity of the polyhedron. It's explicitly not that exactly, but it's a good picture to have in mind when talking about analytic centers. Variable statistics. Yeah, we are statistic collectors, as we saw in the branching presentation. So-called locking numbers. The number of potentially violated rows. It's a glorified number for counting the number of times a variable appears with a plus or a minus sign in an inequality. Like here for this y variable, there are 3 rows that can, if you start from anywhere inside the polyhedron and increase the value of only that variable, that will eventually get violated at some points. So we would say this variable has an up log of 3 and a down log of 2. There are only 2 constraints which could potentially get violated when moving, reducing the number or the value of that variable. Pseudo costs, you've heard a lot about them. Certainly there are ways to incorporate them into heuristics. And conflict statistics, again, the same thing that we used for branching. And finally, some of the global structures. Clique table, same as the clique graph, just different way of storing the same data. Multi-common or any kind of flow structures. Flow structures are very easy to detect heuristically. Someone asked me in the break, what kind of structure, how would you decide whether to look for a structure or not? Rule number 1, it must be easy to detect. Rule number 2, it must be common enough. That's when you would start using it in general MIP solving. And rule number 3, there must be something to derive from it. Okay, the implication graph and the variable bound graph, they're so closely related to each other. I brought an example here. This is like a directed acyclic graph that shows how different bounds of variables connect to each other. So like the lower bound of x here, if I change the lower bound of x, as I see here, for example, this has an impact on y. So this is what this edge on the lower bound of y. If I increase the lower bound of x, I increase the lower bound of y. This is what this edge here shows. I can connect different variables or different bounds of variables via the logic from different constraints to each other and use that to fix variables from left to right rather than start somewhere in the middle, for example, if I heuristically fix variables. Okay, brings us to different types of heuristics. I tend to categorize them into rounding heuristics. So rounding heuristics are heuristics that take the fractional LP solution, change the fractional to integral values and cross fingers. So no re-optimization in between, no frills, super fast. If you have a good rule on which integer value you to drive a fractional value to, that might work. Diving. Diving is something like a single dive. Well, that's where the name comes from in your branch and bound tree. You would apply it to find a heuristic solution, and then you would throw it away because you don't want to keep it in your branch and bound tree for reasons that we will see later. Feasibility type heuristics, I will explain what a feasibility pump is, where you change the objective to drive the solution towards integrality. And one of the most important one, large neighborhood searches. I list pivoting for completeness. They are not really applied anymore in the servers. They are rather from the early days of MIP solving. And the other, axis along which you can split heuristics into different types are start versus improvement heuristics. Start heuristics don't need a feasible solution. They just try to construct one from scratch. They might still be applied if you already know one. So you might throw several start heuristics onto your problem, even if one of them already found a solution. And improvement heuristics take a feasible solution, work with it, try to change something about it to make it, to give it a better quality, to find a solution which has a better objective value. Okay, let's just walk through them one by one. Again, rounding, one of the first things that people come up with. And yeah, one important bit for rounding heuristics are the variable locks. So they are some of the most simple ones, or only work when all of the variables that you are dealing with have one direction in which they have 0 locks. In that case, you are guaranteed that you will find a feasible solution from an LP fractional point if you always round into the 0 lock direction. Then there are others like roundings. There's one rounding heuristic that might violate constraint intermediately. It's what it does is it takes a point. It's not the best example, I realize. So it in each step looks at which is the direction with fewer locks and goes into that direction. Unless there's a direction with 0 locks. That you can keep for later, because that you can always make feasible. And one thing that I would also use this as an example for is a so-called fast fail strategy. That heuristic that I'm talking about, which for whatever reason is called the rounding heuristic in Skip, it doesn't have an extra name. It starts, so I told you for each variable that it considers which would be the direction, the one with fewer locks. And it orders the variables by those where this value is the largest. So you're taking the most critical decisions in the beginning. The hardest decisions are made first. The reasoning behind that is, well, this is the most likely situation where you might mess up your algorithm and not be able to retract one. You want to, if this situation occurs, you want to occur it fast in the procedure. It's okay for heuristics to fail as long as they fail fast. And this you can apply to many other areas of MIP solving, maybe even of life. Try to do the critical things in the beginning. Someone asked me about symmetry detection in the break. Symmetry detection is an expensive algorithm if it finds a lot of symmetries. So it's okay for it to be expensive because it's only expensive when you find a lot of stuff. Symmetry detection will almost always fail immediately when there are no symmetries in the problem. It's a fast fail algorithm. So, okay, diverted a little bit. Really not too interesting. There's different rules. There is even something like random round towards the analytic center. That's maybe the most interesting one. Some of the rounding heuristics, if applied to a MIP, at least would solve one final LP to get the continuous values straight. Then there are fix and propagate heuristics. If you know a little bit about heuristic literature, this would be things like fix, propagate, repair, shift and propagate, feasibility jump. Those just a little bit of name dropping. Fix and propagate heuristics work with some reference point, so they have an integer, potentially infeasible or usually infeasible point to start with, and then they keep all of these variables open. So variables are allowed to move there. And you would then greedily fix one variable after the other. And by which rule you do this, this is exactly how the different heuristics differ from each other. And always when you fixed one variable, you propagate the impact of these fixings. So you try to derive further fixings from that, thereby slowly fixing more and more variables in your point, reducing your search space, which is just the domain cube, so to say, unless you either get into a situation from which you can't retract or until you find a feasible solution. So when I say you cannot retract, I mean that typically what you do in fix and propagate heuristics and also in diving heuristics, which will be the next slide, is once you hit an infeasibility, you try the opposite fixing. You undo the last fixing and try the opposite direction. If this also fails, obviously you could backtrack further, but you don't do this. Like there's one chance to repair something. Everything else is considered too expensive overall. Fail fast. Okay. Diving heuristics. I already mentioned the general idea. They simulate a dive in your branch and bound tree. So you do exactly what you would do there. You solve the IP relaxation, fix a variable, go down one side, resolve the IP, fix a variable, go down somewhere, maybe propagate in between until you hit the bottom and are either infeasible or found a feasible solution. If you run into infeasibility, you would try the opposite side once. That's again feasible, you bail out. If not, you continue the procedure. So why do we do that as a heuristic? You're already doing that in your branch and bound search, aren't you? Well, this is because you are using different strategies there for fixing variables, for deciding variables to branch on. And remember, the idea of branching strategies was to raise the dual bound and to balance the two sides of the branch and bound tree somewhat, to raise them equally. This is why we're using this geometric mean. And this is not necessarily what you need to do when looking for a good solution. In a sense, you want to be as imbalanced as possible. You want to find one direction which is very likely to lead you towards feasibility and another one which might be very bad. For branching strategies, I mentioned that most infeasible branching is a terrible branching strategy. What I didn't mention is there's one that is even worse. That's worse than random branching. That's least infeasible branching. If we build up a branch and bound tree, branching on the least infeasible variable, this will be, again, like an order of magnitude larger than the most infeasible branching one. It's a terrible idea for branching. It's a very good idea for constructing a feasible solution. Be greedy. Something that's close to integrality, try to fix it to integrality and see what happens. That's what's called fractional diving, round the least fractional variable. Guided diving tries to dive towards a feasible reference solution that you already have. That comes from a different part of the tree, so it's not feasible inside your current subproblem, but you try inside your current subproblem to get towards that solution with the hope to find a better one. Coefficient diving uses variable logs again, dives into the direction of your logs, but resolves the IP, unlike that rounding heuristic that I talked on. Line search diving observes the development since the root IP. So if a variable here, like the height, the Z variable, that's been going downwards here, if you see a trend of a variable going from the value it originally had to one of the integer variables to values to one of its bounds, then you just enforce that bound. Okay, before we come to large neighborhood searches, which is like the most important subclass, I would briefly like to mention inner parallel sets, a neat theoretic idea, which is also somewhat practical or somewhat working in practice, is to apply all of these procedures not to your original IP, but to an IP where you, which is move towards the inside. You reduce like 1/2 in every variable, in every direction. And this will, as a consequence, if you find a linear feasible point here, each rounding of that, or the nearest rounding, not each rounding, but the nearest rounding in a geometric sense, will be feasible. More often than not, this inner parallel set MIP here will just be empty. And then you can't work with this. But if it's not, then there's an easy way from solving LP relaxation of this one to finding an integer feasible solution. Okay. First time. Okay, again, this is asking what I think are the key takeaway messages from this first half of the presentation. What are the answers? First question, diving heuristics. Yay, they simulate a depth first search, exactly. And fix and propagate heuristics. Let's see, they typically do not solve LPs or auxiliary MIPs. And then finally, primal heuristics as a whole. They might terminate unsuccessfully. Interesting stuff happening here. So let's look at large neighborhood search, a new category, and one of the most important ones for primal heuristics inside solvers. How can you find good solution? Well, sorry, there's another slide before that, local search. Before we come to large neighborhood search. So local search is the typical combinatorial procedure. It's considering a reference solution, unfixing a small number of variables from there, and then trying alternative values. So you take a reference solution, try to find one that's very close to that by explicitly checking. Like inside the general MIP, for example, for a one neighborhood, literally fixing a single variable is something that's applied. On a general such a thing as a general MIP, doing it for a k neighborhood, for k larger than 1, is very easily getting computationally out of hand if you do this explicitly. I mean, even for a 2 neighborhood for 10 million variables, that's relatively expensive. You might use some structures to only test a subset of that. So 2 opt heuristics are something that's still applied. On more general combinatorial problems like the TSP problem, the Lynn-Kernighan heuristic, which is one of the best heuristics for TSP, is like a sort of a k-opt heuristic with a flexible k. Okay, and then, well, if the new solution improves, you accept it as a new incumbent solution and might repeat this procedure until it doesn't give you anything anymore. To the contrary, large neighborhood search heuristics, well, they consider, again, one or several heuristics, but they could create an auxiliary, one or several solutions, but they create an auxiliary problem that you would never dare to try to enumerate completely, with the characteristics that the feasible set is a subset of the original problem, according to some definition or some rule of how you do this, typically by fixing some variables, adding some constraints, potentially changing the objective, and then performing a partial search on this. So I'm a bit picky here of getting these two things, local search and large neighborhood search, separated from each other. One takes the solution, unfixes a few variables. Like if you have a 10 million variable problem, maybe 2, 3, 4, 5 variables get unfixed and you try to modify them. A large neighborhood search would take the problem, potentially fix something like 5 million, 6 million, 7 million of these variables, keep the other 3 million free, and solve the resulting MIP. Most likely just partially. So in a sense, this is the answer of how do you find a good solution for a MIP? You solve a MIP, but a smaller one, which might be easier to solve and hopefully still contains good solutions. And how do you construct these subMIPs? One of the most basic idea is the Wentz algorithm, where the reference point that you use is the LP optimum, as we will see for a couple other heuristics as well. And then in this LP optimum, just fix everything that's already integral. In many cases, that's like 80, 90% of the variables. Also, if you have general integer variables, reduce the domain of them to the two closest integer values. The result is a mixed binary subproblem, so only binary variables, which is very helpful for many other procedures that we saw today, and solve the resulting submip. If you solve this to optimality, you will have found the optimal rounding of your original point. And in many cases, there is one way of rounding your fractional LP solution. It's just about how to find this one way. Brute forces via a submip solve. Different take on this, the Rinz algorithm. So this does not take one reference point, but hold your breath, two. Namely, the LP optimum, again, and some integer solution that you found previously. And you fix all the variables that these 2 points have in common. The idea being that the resulting search space, well, it will still, if you don't consider like cutoffs to bounding or so, it will still definitely contain the LP optimum. So it will be of some high quality. There will be high quality points in there. And it's still containing the incumbent. So there's at least one feasible solution in there. And it's potentially much smaller than the original problem. Yeah, that's what I just said. Take these two reference points, fix the coinciding variables, and try your best. Local branching is maybe the one that's closest to a local search algorithm, because you actually try to search something like a K neighborhood of a feasible solution. But you don't do this explicitly. You do this by adding a constraint. In the binary case, that's pretty easy. That's like a single knapsack type constraint, where you just require that the number of changes in the binary variables is less than K. So for example, if the 0 was the reference solution, that would be sum over all variables less equal K. And if like it's a 1, then you do like the exchange with the complemented variables. It's a bit more involved version. If it's general integers, you wouldn't, of course, add like these exponential number of constraints here. You would add auxiliary variables that model this behavior. And then again, use your incumbent as a reference point and impose this single local branching constraint. Trivial to linearize for binaries, a bit more involved for general integers, solve the resulting submip. And finally, the crossover algorithm. This takes several input points again, even more than 2 in many cases, namely different feasible solutions that you already found. Like think of the last 3 solutions, last 5 solutions that you found, or all solutions. But if all solutions have like half of the variable assignments in common, it's pretty likely that this will also hold for the optimal solution. That's probably some intrinsic requirement of your model that you didn't detect explicitly, but that is there. So use this for looking for solutions. Warning, of course, if you only do crossover all the time, this might become a self-fulfilling prophecy. Okay, so you start with a reference, a set of solutions as a reference, fix all the agreeing variables, solve the resulting submip, and you can easily think about some different strategies of how to select such a set of solutions to get some diversification, but still also some tendency towards good solutions. Okay, not yet finally, but coming, well, these are definitely some more desperate strategies. Changing the objective, which in many cases means pretty much giving up on good quality if you throw the objective away or change it, but focusing only solely on feasibility. Like the first one, most extreme case, completely drop the objective, make it a feasibility problem. Some problems then, so to say, fall apart. They collapse into a small, tiny problem which remains, because you can apply a lot of presolving reductions which allow you to fix variables as soon as there's no objective, no optimality requirement anymore. The keyword here is dual presolving. You heard this now. In the next lecture, I will talk about dual presolving, and you will know, that was the thing that was helpful for the zero objective heuristic. Maybe even more desperate, inverse it. Try to find a solution that's as far from optimal as possible, to at least find something feasible. Actually, very occasionally applied inside solvers. Or use the local branching logic that's maybe not as desperate in an objective sense. Try to minimize the distance to the incumbent solution after having applied a cutoff that makes the incumbent infeasible for the remaining search process. Or something that I find very neat, but I might be very biased here, is to use the analytic center as an objective. My interpretation here is that you can see the analytic center as something like the average value a variable takes throughout your polyhedron. If this has a larger value, then it's more likely that you will find solutions which have this variable sitting at a 1, thinking about binary problems for a second. So these are variables that I would want to drive towards 1, variables with a very small value, I try to drive towards 0, find a threshold in the middle, how you tear your variables apart, and then use this as an objective. Okay. And finally, for the neighborhood search heuristics, graph-induced neighborhood search. And the idea here is that you, shall I plan this? You're having something like kernel points in your fixing strategy. There's certain variables, a small set of variables where you say, okay, those are the ones for which I decide that I want to fix them and the fixing values. And then I look closely to these variables in the surrounding that are connected to them. I also fix them. You can, by the way, apply this logic in either order. You can either say this is a part of the problem which I want to keep open, and I will fix everything outside, or the other way around. That's the part of a problem that I want to fix. And then I see how are the variables connected to each other via the constraints. So I find clusters of variables that I keep open or fix. I'm actually not even sure in which way I formulated here on the slide. Obviously, this can also be applied on top of other fixing rules. You take one variable with respect to your crossover logic, for example, and then decide this is a variable that you want to fix the neighboring variables as well. Okay, next class of heuristics are the feasibility pump-like heuristics. Most important candidate here is the original feasibility pump. Almost 20 years old, one of the most influential heuristics. There's like 20 more papers on this. Basic idea. So you solve the original LP, then you want the LP optimum. Well, if that is feasible, you would be happy and stop. If not, well, if cycling, and let me skip over this, the important next step is that you change then the objective to minimize the distance to this infeasible integer point, the distance in Manhattan norm, in one norm. So that again will be a linear problem, definitely for binaries. For general integers, you're facing the same situation as for the local branching. For example, you might resolve this via auxiliary variables. And then solve the LP again. So where this was our integer point, the closest point on the surface of the polyhedron in Manhattan norm, not the Euclidean norm, is this one. You round it again. In my example, we then would be feasible and happy. You might quickly observe that this might run into some kind of cycling behavior. If we change this polyhedron a little bit, the closest point would again be the optimal one. This is why you need to do something about cycling. In the original version, there was just some perturbation. You flip some variables around. Okay. There's a lot of variants, as I just mentioned, of this. The first modification to this was using auxiliary variables for general integers. So the very original paper was only on binaries. Then there's the objective feasibility pump, which tries to address one of the main drawbacks of this. It's an objective changing heuristic. So from step onwards, you give up on objective quality. You're just minimizing distance, right? But it's not clear what this means in the objective space, so to say. What was suggested here for the objective feasibility pump is to use a convex combination of the original objective and the distance function. In the beginning, in the first few iterations, focus on objective quality, gradually shift to the original feasibility pump algorithm and try to drive these solutions closer and closer together. Yeah, why not? One very interesting observation is that this, by chance, we actually didn't think about this when we started the project, that this can very well help to recover from cycling when you're changing the objective over time. So you might get rid of this perturbation set in certain situations. Then there's the feasibility pump 2.0, which applies dominant propagation as part of the procedure. There's some peculiarities that you have to take care of when the objective is changing during your propagation. But it's again a quite significant improvement over the original behavior. These things very well combine with each other. There's many more variants. Finally, I would like to talk about what is the real value of primal heuristics. I think essentially I asked this question in the beginning of the presentation. Why do we need this? And how can we prove that they are so valuable? How to measure the added value of primal heuristics? Pretty much every, MIP paper, presentation, and so on. The gold standard that you look at is the time to optimality. A procedure is good if it improves the time to optimality, if it helps you solve your problems faster. For people who like to work on primal heuristics, the bad news is that heuristics, I mean, the time to optimality mostly depends on the dual bound. So that's not, I mean, if that's the measure that you're looking at, then primal heuristics are indeed not that important. Still, they are a very important ingredient of MIP solvers. And how can we quantify this? Well, one could look at the time to the first solution. Primal heuristics excel in this. Like a MIP solver with primal heuristics is typically like 2 orders of magnitude faster in finding a first solution than a MIP solver that doesn't employ primal heuristics. But this completely disregards the quality of the solution. To give you an actual example, in MIPLib, about 20% of the instances allow for an all-zero vector as a feasible solution. That's a very easy to find solution. You can just check it before you start anything in your solver. So 0.00 seconds to find it. Also, it's completely useless. That doing nothing is a feasible solution for some problem. Well, great, you knew that to start with. That will never be useful in practice. Time to best solution, yeah. Again, maybe not the perfect thing. So the question was, is there some combination of all these measures? And the answer is yes, there is. And it's a measure that's pretty useful in practice, because to the best of my knowledge, many major MIP solvers use this today as a measure for evaluating their processes, their progress in their software. And that's a primal dual integral. Comes with some math formula here. So what is this doing? We look at what's called the primal dual gap of a solution. And we're getting some special cases out of the way. So here assume x star to be the LP solution, x tilde to be an n integer solution. So if these both coincide at 0, then it's considered 0. If they have different sign, you say the gap is 100%. So all of these are special cases to make things work in the end. The important part is the last one. What you consider the gap of a solution is the gap between its objective value and the dual bound, the global dual bound of the problem, divided by the larger of the two values. Ambros's first talk, when he was jogging from zip to TU, he talked about that the solution he got from Google Maps is 18% away from the dual bound that he got from the B line. That's exactly this. The 18% is what you would get here as a primal dual gap between those two things. Okay, the primal dual gap measures the quality of one solution. So what you can do is observe the development of both your primal bound and your dual bound over time during a MIP search. And from a heuristic point of view, this search process is good if this gap gets closed early. Or differently speaking, if this area here is small. So the primal dual integral is computing the area between these two curves. So the integral over the primal dual gap over time, or just it's taking that's a glorified expression for taking a sum here, integrating over a step function. It's a step function, right? Because it changes at discrete points in time. It's easy to compute, and it's a good measure because it favors finding good solutions quickly. That's what matters a lot in practice of MIP solvers. In particular for problems that you can't solve to proven optimality within any reasonable time. It considers each update of the incumbent, not only the final solution, when and where you found it, and of the best bound also. And there's even like an interpretation of it that it gives you something like the expected solution quality if you terminate it at an unknown point in time, which from a solver perspective is realistic because you don't know what your users are doing and which time limits do they employ, how fast is their hardware, and so on. I'm running over time again. I would like to mention one or two more things that many solvers have something like a heuristic emphasis mode. I mentioned this already. The beauty of MIP is that we can solve problems to proven optimality. Practitioners often say, Yeah, but not in a reasonable time. Just give me some good solution as quick as you can. A heuristic emphasis mode of a solver, focus on primal heuristic would do exactly that. And the measure of how you tune the setting of a solver, what we use is the primal dual integral. The technology is a clever tuning of all your different heuristics, more neighborhood searches, some non-default heuristics, more frequently applied, and so on and so forth. A little more in this and much more on all the different kinds of heuristics in an upcoming book that I wrote together with Andrea Lodi, who will be here on Monday, and Domenico Salvanin from the University of Padua, scheduled to be released in somewhere in the first half of 2025. Advertisement slide over and quiz time. Okay, story. LNS stands for exactly large neighborhood search. What's the idea of crossover? T. That coincide in all or some integer solutions, but not in the incumbent and the AP optimum. This is called RINS, relaxation-induced neighborhood search. And finally, the primal dual integral. Hey, it considers each update of the incumbent. Thank you.